Hello, this video I'm going to show how to solve this problem involving this thermodynamic process. I don't really think this thermodynamic process has a name. It's just from this P initial to this P initial and V initial to this P final and V final via a constant straight line. I have no idea how you actually set up this thermodynamic process in real life. It's kind of a bizarre thing to have happen as the pressure and the volume both increase. But alas, we can pretend it happened. Okay, so if you were to somehow set up this process, how much work would it do? So question number one, how much work would it do? So we can do this, well, work is PdV. Work is PdV. So we basically want the area under that curve. You can think of that as the area of the square and the area of the triangle, or you can just think of it as you can just take the average pressure times the change in volume. You'll notice that triangle and that triangle just kind of cancel each other, so that this area here will also be the area under the curve. Okay, so we can just write that down. Work is equal to the change in volume, V final minus V initial, times P final plus P initial over 2. So that's the change in volume times the average pressure is what it turns out to be the work for that particular process. All right, now let's talk about how much heat was added to the gas during this process. The way you want to do this, well, we got work. Change in energy is pretty easy to get to because we can get it from temperature, and from those we can use the first law of thermodynamics to infer the heat. The change in internal energy is equal to the the heat you add in minus the work done out. Because this is doing work out, it's getting heat in. It needs a lot of heat in because it's going to go to a higher temperature. We want to solve for Q in. So Q in, the thing we're looking for, is delta U plus work out. We already figured out work out. It's right up there. Let's figure out what Q in is. Q in, you can infer from the temperature because U is equal to, and this is a monatomic ideal gas, so 3/2 NKT is the internal energy. Said differently, delta U is equal to 3/2 NK delta T. So we can write Q in as 3/2 NK delta T plus the work, which we already have up there. Okay. Let's see, what should we do next? Well, basically, we have work. We don't know what delta T is. If you look at the things that were originally given, we were given the P's and the V's, but not the T's. You can infer them based on the ideal gas law. P V equals NKT. So you can do that for the initial temperature and the final temperature, and you'll see that NK delta T is P initial, or P final V final minus P initial V initial. So we can write this as Q in is equal to 3/2 P final V final minus P initial V initial. And then I'm going to plug in work plus, so work is at the top of the screen there. So you have V final minus V initial times P, oops, a little better, P final plus P initial over 2. And this is actually a correct way of writing the answer. It's got the thing we're looking for, Q, in terms of the P's and the V's. It's kind of ugly though. If you do some algebraic manipulation, you can get this down to Q in is equal to 2 P final V final minus P initial V initial plus 1/2 V final P initial minus P final V initial. So that's an alternative way of writing the answer. Okay, so we basically have the Q in. So we found work, we found heat. The third thing it asks us for is change in entropy. So entropy is a little bit more tricky because if we remember what entropy is, 3 delta S, well, let's actually write it as ds. ds is equal to dq, the heat, over the temperature. But as we add more and more heat, the temperature keeps increasing. Which puts us in the bizarre case of each little amount of heat we add gets us a little more, take that little amount of heat, divide by the particular temperature it's at that point, and you get the little change in entropy. So we can't just take our Q in and divide it by temperature. What temperature, after all, would we divide by? The beginning in the temperature, the end temperature, the average temperature? Instead, we actually have to deal with this via an integral. So the total change in entropy will be basically integrating dq over t, where t will change as we add heat. Okay, so which basically we want to start the process just like we did up here. We had q in is equal to delta u over dw. We can write the differential form of that, where we like, if we add just a little bit of heat, dq in is equal to du plus dw. Right? Yeah, if you add just a little bit of heat, you get a little bit of, it'll equal the change in temperature, change in internal energy, plus the work done. Okay, so these are a little more handleable. We can deal with du in the same way we did earlier. Du, u is 3/2 nkt, so du is 3/2 nk. N and k are constants, they just come out. dt. Okay, well, that's kind of nice. And work is pdv plus pdv. Remember, work is force times distance. You multiply and divide by area, force times distance becomes pdv. It's the pressure on the, say a piston times, or the force on the piston side, how far it goes, multiply and divide by area, you get the pressure on the piston times the change in volume. Okay, so that gives us the Q for this particular process. Let me write this in a little bit better handwriting. NK dt. dW is NK dt. We're not given N and K. Well, actually, no, this is fine. This is dq. We want to find S, not Q. So ds is equal to, we'll just divide this whole thing by t. 3/2 nk over t dt is equal to p over t dv. So basically we took, to get ds, we need dq over t. Okie dokie. There's one issue left, and that is that t changes as we change v. So if we integrate this to get the change in entropy, this term will be fine because it'll be t dt, 1 over t dt. That's fine. T changes as t changes. That's cool. That can be handled by integral. However, the t will change as v will change. So we need to write t here in terms of v. So if you remember, pv equals nkt. We can divide by t and divide by v, and we get p over t is equal to nk over t, nk over v, like so. Yeah. So we can plug that in there, whoop, and we get the change in entropy. A differential change in entropy is 3/2 nk over t dt plus nk over v dv. This is kind of an interesting formula. We can just talk about a bit about what it means. Basically, entropy comes from two different places. If you want to think about this in a ways of arranging the system, the real definition of what entropy is. If you add heat to a system, raise the temperature of a system, there's more ways of arranging that those joules of units of energy among the molecules, the gas molecules. So if you raise the temperature, you raise the entropy. So this term captures that. Also, if you expand the system, you can arrange, there's more ways of arranging the molecules because you can arrange them, in a bigger area. Imagine doubling the volume of a system, for example. Each molecule, now you have twice as many places you could put it. So there's lots of more ways of arranging the system. So this right here is kind of the entropy due to ways of arranging heat among different molecules. And the second one is the ways of arranging the molecules in more air, in more volume. You can kind of see where this is related to the actual definition of entropy, which is number of ways of arranging the system. And we can integrate it to get the entropy. So ds is equal to 3/2. You can take the nk out, nk integral of 1 over t dt from t initial to t final plus nk, the integral, that integral, the integral from v initial to v final dv. So that's that integral. We can now do this integral, these two integrals. We get s, the total change in entropy, is equal to 3/2 nk. The integral of 1 over t dt is natural log. So natural log, if you put in the final and the initial, that's t final over t initial plus nk. Whoops, I missed a term. I forgot my 1 over v. 1 over v dv. Okay, that's better. The integral of 1 over v dv is natural log of v final over v initial. Okay. So this is almost there. Once again, you can kind of see this. This is the change in entropy due to more ways of arranging heat energy among the molecules. This is the more ways of arranging those molecules in a larger volume. We have both of those. In this particular problem, we're not given T final over T initial. We're actually given P's and V's. So we can use the ideal gas law to relate the temperatures. The ideal gas law says that T final over T initial equals P final V final over P initial V initial. To see that, take PV equals NK delta T for all final, divide that by all initial, the NKs cancel, and this is what you get. We can then plug that into there. We get delta S is equal to 3/2 NK natural log of P final V final over P initial V initial plus nk natural log of v final over v initial. That's kind of cool. And that is a correct answer. We can actually simplify this. You can use the laws of natural logs. Remember, if you have two things multiplied inside a natural log, you can break them apart into two natural logs that are added together. Ln of a times b is equal to the natural log. Come on. Natural log of a plus the natural log b. Remember that thing? Okay, you can use that here to break apart our p's and our v's. We can then combine the v's into this term. So we can also alternatively write this as 3/2 nk ln of p final over p initial plus, and this would be 5/2 nk ln of v final over v initial. So that's another way of doing this. Okay, so there you have it. That's that is how to write the entropy change for this particular system. For this particular process that we had, where we go from p initial v initial to p final v final. Thanks for watching.